Well, hello everyone. Me again. I bet you were not expecting that. So our next speaker, Reid Haefer, is ready to take our virtual stage to walk us through the process of leveraging data to decide which sidewalks should be repaired and when, and the role of Shiny in the decision-making process. It sounds pretty amazing to me. So the story goes that the city of Burlington in Vermont faces a problem. Because of a limited budget, the officials need to triage the some 130 miles of damaged sidewalks, and to prioritize the repairs, the city used innovative data collection technology and created a custom interactive decision support system to assist with that task. I don't know how, but somehow I got excited about repairing a sidewalk. That. So Reid is a consultant at Resource Systems Group and specializes in using data science to make sense of complex data. And a friendly reminder, if you have any questions, feel free to ask them in that chat. And the stage is yours, Reid. Thank you.
All right. Well, thank you. And thanks everyone for tuning in. Again, my name is Reid Haefer with RSG, and I'm going to be talking about a case study of a Shiny app I created to help figure out which sidewalks should be repaired. So again, Reid Haefer, consultant at Resource Systems Group. My background is in urban and environmental planning. Like many, I started using R in a graduate school statistics class, and subsequently I've been using Shiny in my career for the past 8 years. I work at RSG, and we're an analytics firm that works within a variety of different topical areas, but we specialize in the built and natural environment. In this case, for this project, we're talking about planning transportation infrastructure. We create data, we collect data, we create predictive models, and then we use those data to help answer important questions. And as part of this work, I create analytical tools. So a little bit of background on my presentation. So first, I'm going to give an overview of the project in general, and then give an overview of the tool I created. I'll follow that by highlighting some of the notable tool features, and lastly, reflect on some of the takeaways from the process of creating this tool. Throughout the presentation, you can see some photos in the background, like you see here, of the actual sidewalks that our client is hoping to fix. So RSG was hired by the city of Burlington, Vermont, to help the city make decisions on investing in infrastructure upgrades for their sidewalk system. Vermont is a medium-sized city in the Northeast United States. They have roughly 130 miles of sidewalks, which are in all different types of physical conditions. So the Public Works Department has an existing program where they devote funds on an annual basis to repair those sidewalks. And they wanted RSG to help them improve their system and to create an updated data-driven framework for deciding which of the sidewalks should be repaired. So the first step in the process was acquiring the detailed information about the physical condition of all of the city's sidewalks. Burlington contracted the company PathView to employ their PathMet technology, which you'll see in the picture. PathMet is a manually propelled stroller-like tool that uses GPS, cameras, lasers, and sensors to collect sidewalk condition data. The city utilized this tool and trucked it around all of its 130 miles of sidewalks to produce a large geospatial data set. The data set consisted of 70,000 10-foot line segments with a variety of attributes for each of those 70,000 line segments. Once the data set was acquired, the question was how to use this data set to figure out which sidewalks should be repaired. As we pondered this question, there were several important considerations. First, the Public Works Department planned to review the sidewalks annually and make investment decisions into the future indefinitely. So ideally, both the framework and any sort of analytical methodology needed to be both repeatable and sustainable. They also wanted the sidewalks to be prioritized based upon both their physical condition, but also their location. For example, sidewalks that were located in the downtown or in low-income neighborhoods should be prioritized. They also wanted the system to be data-driven, and so that every single sidewalk segment would be given a quantitative score so that all the sidewalks could be compared to each other. Lastly, one of the overarching questions was how to determine which of the characteristics of the sidewalk should be given the highest weight when determining a score. For example, how should its location compare to its physical condition when deciding which ones are more important? The solution to this challenge, a Shiny application. The city was open to considering various approaches to the problem, and I thought Shiny would be an appropriate solution for several reasons. First, I knew that we could spin up an application in a relatively quick time frame with no costs. Because the framework hadn't been developed, I knew that the app would need to be customized and modified in an iterative way. I also knew that there would be a focus on both spatial and tabular data, and that those two types of data would need to be deeply integrated. In addition to Shiny, I knew that there were several R packages that can make this happen. For example, Tidy Census is great for socioeconomic data. MapView is great for plotting large spatial data sets, and Tidyverse and SF, which are some of my go-to packages for pretty much any analysis I do. So I dove in and started creating a Shiny app. The eventual tool that I created had three main components. First, the core part of the tool was the prioritization methodology that allowed users to assign weights to different elements of the framework, rerun the model, and then review the results. The second part of the app was the general purpose analysis tool designed specifically for public works staff. The analysis tool allows the staff to explore the large underlying data set and answer key questions that they're interested in. And lastly, there's a documentation page that makes the entire process transparent and includes written documentation, instructions, metadata, and an area where you can download different pieces of the data. As a public sector project, everything needs to be transparent and not a black box methodology. The tool is hosted on shinyapps.io, so public works staff can quickly access the tool via an online URL and share it with their colleagues or members of the public. So part of the utility of Shiny for this project was actually developing the framework itself, which are the assumptions and logic behind deciding how to score and prioritize each segment. In contrast, for the creation of many Shiny tools and projects, there's often a framework that's already been created, and the main purpose of the project is simply to daylight and implement that framework through a user interface. This project was a little different. Like I said before, one of the biggest unknowns was deciding which characteristics of a sidewalk were most important. For example, should the running slope of the sidewalk be more important than a cross slope? Should sidewalks next to bus stops be higher priority than those next to schools? So the first phase of the tool development process was creating an interface where the user could experiment with different weights and then observe how those different weights scored the sidewalk set differently. The tool has numeric inputs for all the different categories that can be modified. Then sidewalk data is processed in the background. Then the sidewalk scores are visualized instantaneously. We worked with public works staff to play around with these different inputs, which eventually resulted in the final scoring framework for all sidewalks. The resulting framework is somewhat complex, but meets the specific needs and interests of the Public Works Department. The framework prioritizes sidewalks in three different categories. First, individual 10-foot segments are prioritized, entire blocks of segments are prioritized, and then streets that don't even have sidewalks are prioritized. Each of these three framework categories requires slightly different logic and different code to implement that logic. The sidewalks are scored upon several characteristics of their physical condition. This comes directly from the PathMet dataset that we collected with the stroller. They're also scored according to characteristics of their physical location within the city. This physical location data includes socioeconomic aspects of their surrounding built environment, which comes from the Tidy Census package and the census data. And we also bring in other external data sets such as schools, transit stops, and senior centers. This final framework will be used by the city on an ongoing annual basis to actually carry out repairs to these sidewalks. So given that many aspects of a sidewalk's location are important, the tool needed significant geospatial analysis capability. As I mentioned before, there are 70,000 10-foot sidewalk segments in the city. Here's an example of the type of geospatial processing that the app contains in various elements. This type of process is reran in the background of the app, every time the user changes the priority weight and reruns the framework. This example shows how the tool applies a score to sidewalks that are adjacent to busy bus stops. It involves bringing in tabular transit ridership data, converting that data to spatial objects, applying a walk-based buffer to busy bus stops, and then scoring the sidewalks that are within that 5-minute walk of busy bus stops. So this is the type of analysis where R and Shiny are really powerful. At the same time, this analysis is relatively simple to implement and can be embedded within an interactive app that users can utilize in an interactive way. As I mentioned before, the core piece of this project was assigning an actual quantitative score to all 70,000 sidewalks in the city so that the Public Works Department could decide which ones to fix. This page shows the final prioritization segments within the Shiny application. I think one of the ways that this app is really powerful is that it allows users to understand the sidewalks in many different ways. It includes a photo of the sidewalk, it includes an interactive map of its location, and an actual searchable table with the actual address and the scores. These features are relatively simple, and they're enabled through powerful packages such as DT Data Table and Map View, but they give the user the ability to explore a relatively large and complex data set very quickly and easily. So here's an example sidewalk at 206 Maple Street, which is one of the highly scored sidewalks. As you can see in the picture, the sidewalk receives a high barrier score because of its deteriorating physical condition. It also receives a relatively high activity score because it is located adjacent to a variety of elements that the framework has deemed important. Based upon this score, this is one of the sidewalks that the city will plan to repair next year. The tool makes it very clear and transparent to city staff and members of the public why this investment decision was made. In addition to the prioritization framework, the tool contains an analysis module. The module consists of a variety of query features that allow public works staff to answer various questions. City staff get questions from members of the public, members of the board, or other staff on a regular basis. Notably, they get inquiries from the members of the public all the time asking, why aren't you repairing the sidewalk in front of my house? They also have to prepare regular reports and presentations that give status updates on the sidewalk program. Therefore, we designed the query tools in a way that are both flexible and open-ended, but also specifically targeted at the questions that staff are interested in. And I think these query tools show off some of the strengths of Shiny. There are user-defined sliders, numeric inputs, and text boxes that are dynamically connected to underlying both spatial and tabular data that generate visualized results on the fly. This tool capability will replace hours of staff time where they would previously be loading the data into Esri software and conducting cumbersome analysis on a repeated basis. There are a few takeaways from the process of both designing and implementing the Shiny app. The first is related to the actual app development process itself. The Shiny app was actually not part of the original project scope. The scope was simply to create a sidewalk prioritization framework and then carry out that framework one time. But by introducing the Shiny app, the city was able to iteratively define a framework, and now they have a tool that they can use continuously into the future to monitor and score sidewalks rather than having to do an annual analysis of data. It's a much more real-time framework than they were previously working with. But the process for developing the app was very nonlinear. While this introduced some uncertainty in the project, it allowed flexibility to create something that truly fit the city's needs. I think if a client is amenable to an open-ended process, it can really yield useful results. Shiny can be useful even when you didn't anticipate it. Shiny is a powerful framework that can yield unexpected results on a variety of projects. I think the other takeaway is transferability about this type of project to other organizations and projects in general. So at RSG, we work with a lot of public sector clients, and I know in the public sector, there are many agencies who have different sort of prioritization processes for things like transportation investments, public spending, and budgeting. The Shiny app I created has a relatively basic structure where sidewalks could be substituted for things such as transit routes or other spatial features. And then priority weights can be modified to other types of priorities that a city could be interested in. This type of tool has a relatively high ratio of tool features compared to the underlying code, infrastructure, and startup costs. There's a lot of ways to characterize this. One way would be the parsimony factor. From my experience, there are a lot of complicated spreadsheets out there that are attempting to do similar things that I did in this Sidewalk Shiny app. Those spreadsheets give people a lot of headaches and require lots of time to modify and keep up to date over time. I believe that this type of Shiny app could benefit lots of other organizations that are looking to understand the trade-offs of different decisions and priorities. For example, in the future, if the city of Burlington decides that the framework should be modified, they don't have to go ahead and do a large-scale update their process. They can simply go into the tool, change the weights, rerun it, and observe prioritized sidewalks with a different set of assumptions. At the same time, the tool is hosted on shinyapps.io and gives Burlington Public Works staff the ability to access the tool quickly and from anywhere without having to access a spreadsheet, a computer, or a local server. I think this tool is a great example of a modern prioritization process and tool that lots of other organizations could really benefit from. So with that, that's the end of my case study, and I'd be happy to take any questions from anyone.
Thank you so much, Reid. I think I have to start with one question that everybody is wondering about. Is the cat okay?
Yeah, the cat's outside the door. She's fine.
All right. I thought so. Just making sure. So first, let's start with a question I've been wondering about. And how often is the physical data run again or recollected? Because I assume after a while the damage factors will change.
Yeah. So they collected this large data set, and like I said, every year they'll go out and fix some sidewalks. So after those sidewalks are fixed, then the scores for those sidewalks would essentially be 0, right? Because they don't have any physical detriments. They still are prioritized based upon their location, but because they don't, they're very high quality sidewalks, they don't require any upgrades. And so they'd be very low on that list. So essentially over time, based upon the exact same data set, the sidewalks will be prioritized and the ones that are fixed get dropped to the very bottom of the list. In theory, maybe in 5 to 10 years, it would make sense to actually do a new collection of actual data, because it takes a while for sidewalks to deteriorate, right? Mm-hmm. They're concrete and asphalt. And so it's not something that would necessarily change on an annual basis, but maybe after 5 to 10 years, they could collect a similar data set and rerun the tool with that updated data.
Awesome. I think that's really cool use case, and I've seen voices that everybody would like this, or everybody's city council would love this app. So a question that came up in the chat from Ritesh is the code available anywhere for this app, or is it closed off?
Yeah, I think right now the code is in a private GitHub repository, and we're in the process of kind of finalizing this contract with the city and wrapping up the project. So once the project's wrapped up, the code will be available. But honestly, in the meantime, I could probably make it public anyway. So yeah, it'll be on GitHub shortly, and I can anyone who's interested in it, just reach out to me.
All right. So there's a question from Chris about the performance of the app, because did including those photos and being able to see through them, did it noticeably slow down the app?
Yeah, I mean, the app performance is probably the biggest challenge in general. And I would say yes. I think this app could be optimized in a variety of ways. And I think that, that previous presentation we were just watching is something that could be integrated as we finalize the app, both the pictures and, utilizing 70,000 geospatial line features, both of those, in addition to the actual processing that's happening, because there's a lot of reactive objects in this application. All those things make a speedy app pretty challenging. And so I'm definitely going to take away lessons from the previous presentation and others to increase the optimization of this app.
All right. And could you give us an indication? That's a question from Catherine Parkinson. How long did it take to get the MVP done for this app?
To create the app?
Mm-hmm.
Yeah, like I said, it was a very non-linear process in that, I was able to spin up the basic app, within a few weeks. But then there was like a, several month-long process of, adjusting it and adding more features. So the app was really created on a, kind of a piecemeal fashion where we would just add feature after feature, make revisions. But, from start to finish, it was about a 6-month process to get to the final product.
All right. Just looking at the time, I think we have space for 1 or 2 more questions. So Chris Amphlett is asking, did you set the default weights, or is it the user required to set them? And if yes, how did you choose those?
Yeah, so essentially the default weights equate to what we ended up deciding the prioritization framework should be based upon. So in the end, there's like a singular framework that has a variety of calculations, and those calculations include these specific weights. And those are the weights that come up in the tool by default. So when the city is using this tool, when they open up the tool, it contains the final prioritization logic that we decided upon as the default weights in all the different, input sliders and things like that. But like I was saying, if the city ever decided in the future they wanted to change their framework, all they would have to do is modify those weights to reflect maybe new assumptions that they're interested in, and then automatically all the sidewalks would be reprioritized again based upon those weights.
All right. Thank you so much, Reid. That was amazing. It's not only a beautifully looking app, but also it's very useful. Thank you for the presentation, and let's move to the next one.
All right. Thank you all.